Let's start. I'll present Karta, basic currently Eyal plugin in Python. My motivation was I usually analyze huge firmwares, and we want to find open source libraries inside them. We want to find OpenSSL, EPNG, zlib, GSOP, like our printer, and we want to find it automatically instead of me reanalyzing NetSNMP over and over again. I couldn't find or use practically current solutions because if you read the terms of dynamics of BinDiff, they say that more than 100,000 functions and they crash. And if you want to try other solutions, such as Diaphora, for instance, it will take roughly 90 minutes in my firmware, in this 60,000 functions firmware. It will have a database of 3 gigabytes and it will crash either. We need another solution, something that will fit the size of the open source and not the size of the firmware. Usually, the complexity of most of the tools is, it depends on N, which is pretty large, is the size of the firmware. We want a tool that depends on K, the library size. zlib has roughly 100 functions, so it should find it fast, and it shouldn't take 2 hours and crash. Essentially, we want to map and match the functions we can see over there, which is much smaller than the entire graph of the firmware. If we zoom in, we can see that we have inside our library, we have files. The compiler compiles the first file to an object file, after which it compiles the second file to an object file and put adjacent in the binary blob, after which you have the third file and so on and so on. If we have the source code of the open source, which we have, and we compile it on our own, we get the object files for each file. If we take the data of what functions are positioned in each file and we try to geographically locate them in the binary, we could do a much faster solution instead of searching for function A from file B all over the firmware. We can find the file A.o. We know what functions we should find there, and we can look for them only in this tight region. Karta is Russian for map, and essentially we want to map our firmware. What we start with is that we search for anchor functions, functions with unique long strings, unique constants, cryptographic constants, and we find them as representatives inside the library. After we found anchor functions, we essentially know where the library will reside in the firmware, and we can zoom in. If you have 100 functions, we have roughly 200 candidate functions and not 60,000 functions we'll need to compare. So it's much faster. After we have found representatives, we need to find the borders of the files. So we have rough representatives of several files, and it's get better and better once we match and compare additional functions. So we can, if you take a look at several of the files, we'll find the exact borders, we'll find additional files, and once we matched all of the files, we know how where the library is and what are the functions. Let's look at it in action. This is the firmware of HP's printer we showed yesterday. If you want to find libpng, for instance, I can't skip the list of strings because that's IDA. Once we have the list of strings and an initial const search, we'll find the anchor functions and zoom in on libpng. Soon enough, we'll identify that it's a specific version of libpng using an identifier plugin. IDA is slow. We have the version of libpng. It found all of the anchor functions already, roughly 40 functions. Now zooms in and analyzes only the functions in the relevant scope instead of all of the functions in the firmware, meaning that it will be much faster than analyzing a 3 gigabytes DB if it was the FROM. This is actually the slowest part. Once Eyal finished analyzing the specific functions, it finished it all. And in just 5 seconds, it analyzed all of the binary functions in the chosen scope, and now it will start matching the functions themselves. And we're nearly done. So, on the way we found library functions, external functions such as str2d, memset, free, crc32, inflate, and strlen, because libpng uses them, and we can derive their addresses. But most important is that we found libpng. We have anchor files, we have a lot of other files, and if we look on it, we can see that there are exact matches all over. The only functions we missed are functions without extras because no one uses them and we practically don't care. If we look closely, we can see that when I manually analyzed it, I missed some function here, sub something, and it told me it should be png read init 2. Before it, we have png read init. And after it, we have png read init 3. So the plugin is actually better than manual analysis of the functions. And that's it. You right click, you import all of the symbols, and you have all of the open source. On this firmware, it worked on OpenSSL with roughly 3,000 functions in the open source with roughly 10 false positives. That's it.